So we're going to start talking about infinite series. Series is different than sequence. Series refers to a sum. A sequence is a list of terms, right? So if we said a sequence, a sub n, that would be a sub 1, a sub 2, a sub 3, a sub 4, listing all the way up to an a sub n term and possibly continuing on. But a series says that we would take those terms and add them together. A sub 1 plus a sub 2 plus a sub 3, continuing along to add an nth term, possibly an a sub n plus 1, and continuing on. Okay, so we want to understand the meaning of an infinite sum and also to develop methods to calculate it. The sum, the series that I have written here represented as a sum, is the sum, if I erase this end part, that means the sum of the first n terms. Okay, this is an ordinary finite sum, and it might be, since it's finite and it doesn't go on forever, it can be referred to as a nth partial sum. So some sums, they approach limiting values. And when we say that things approach limiting values, we mean that they converge. So an example of something like this might be 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, right? And I mean, we can keep going on. So what you're noticing, though, is that the terms are becoming sequentially smaller, and this is something to us that might indicate convergence. And so I grabbed this picture from our text. So if we look at the sum of the first term alone, we get 1. The first two terms, that sum, we end up with 3/2. The first three terms, adding up those, we end up with 7/4. Okay, so we start to look for patterns. And as we look at adding up to the nth term, we can create a value which looks like this: 2 to the n minus 1 over 2 to the n minus 1. So, breaking down this pattern and looking at what's happening here, we can come up with a suggestive, not entirely correct, but an expression that represents a partial sum. And so a partial sum goes to an nth term as opposed to an infinite sum, which would go on forever. So what we have here is that there is indeed a pattern, and these partial sums, they form a sequence with this 2 minus 1 over 2 to the n minus 1 representing that nth term. And so, looking at this, what we begin to notice is that the sequence of partial sums converges to the value 2. And we can say that since we know, or since we can, determine that the limit as n goes to infinity of 1 over 2 to the n minus 1 equals 0. So, looking at this sum we have up there, if we looked at those terms becoming infinitely large, this last term would disappear if you plugged infinity in, because 1 over 2 to the infinity, that's a huge number. 1 divided by a huge number, we know is 0, or tends towards 0. So what we can say here, the sum of the infinite series not a partial series, but the infinite series, which would be 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, going all the way on to plus 1 over 2 to the n plus 1, that sum is going to equal 2. And I grabbed this visual to pull in to help us think about adding these terms, 1 plus 1/2 plus 1/4 plus 1/8. You notice they're getting smaller and smaller and smaller. And so it's maybe a little bit easier for you to see. So as those terms become smaller and smaller, significantly smaller in size, we can generally assume we're going to have a convergent series. So we're given a sequence of numbers here, a sub n, and expression in the form of a sub 1 plus a sub 2 plus a sub 3. So adding all of these terms. And this sequence, when you sum it up to the nth term, represents an infinite series, right? We have what is called an nth term. And the sequence defined by the list of all those sum terms represents the, this guy right here with the curly braces means we're adding up all of these sums, and it's the sequence of partial sums of the series. So S sub n right here is the nth partial sum. If the sequence of all of those partial sums converges to a limit, then we can say the series converges and its sum is that limit. So in this case, adding up all of those terms, that would represent the sum of all of the terms from 1 to infinity. And then if it doesn't converge, obviously we say that it is divergent. And so I've pulled in 2 pictures here that kind of help us think about what we're looking at. The sum of a series of all these positive terms could be interpreted as a total area of an infinite collection of rectangles. So we have all of these rectangles here. And if the total area of rectangles is finite, so it really, they're becoming these insignificant values that we're adding as we expand out, then we would say that would represent something that converges or is convergent. Whereas if you look at this second example, they aren't really starting to become insignificant. They're still all have a reasonable area, and they appear to be unbounded. Okay? So the total area can be infinite even if the area of rectangles is decreasing. So even though they're going down here, this is still representing an area, an infinite amount of space, which we would say is divergent, or it diverges.